Okay, so we saw last time that Lewis wasn't so dumb. He knew about Earnshaw's theorem, but he thought that, but he still thought there was an octet of electrons around the nucleus. How could he think such a thing? Because if you have inverse square force laws, you can't have a static positions of charged things unless they're right on top of one another or blown apart. So what did he think? That it's not an inverse square force law, that Coulomb's law breaks down when you get to very small scale. And J.J. Thomson thought the same thing and wrote here this two terms here. The first one is Coulomb's law indeed, but there's this other thing, C over R. So as long as R is very big, you don't care about that term, right? As long as it's very big compared to C. And C is a distance that's something like the size of atoms. So once the distance of the things that are interacting with one another, the electron and the nucleus say, once they get near the distance C, then this C over R thing becomes significant if R becomes very small, right? And it even changes the sign, right? So what was attractive becomes repulsive. So that would do okay then for a structure, right? That was in 1923. In 1926, just 3 years later, quantum mechanics came along and showed that Coulomb's law was just fine. Nothing wrong with Coulomb's law. It goes to much, 10 to the 20th, smaller distances than the size of atoms. Coulomb's law still works, right? What was wrong was the way they treated kinetic energy. Because kinetic energy, quantum mechanics reformulates, so it gives you electron clouds. And so what's a cloud is not the positive charge. Remember, J.J. Thomson had a positive sphere of electricity in which he embedded the electrons. What's a cloud is the electrons, and nuclei are put in it to make molecules, right? So it really is, he was right about plum puddings. He just had the charges backwards. Not many people give him credit for that. So cubic octets of Lewis and ad hoc electrostatic force law like this C over R term in there soon disappeared from conventional chemistry and physics, immediately in fact, I mean within a month say, okay? But the idea of shared pairs and lone pairs that Lewis came up with remained useful tools for discussing structure and bonding. Right? So we still do them, and that's why you did problems today that had to do with that. Yes, Nico?
Yes. Can you explain the kinetic energy?
Yeah, but I won't do it for a week still, because it takes a little while. Okay? Okay, so Earnshaw said there's no structure of minimum energy for point charges, right? That is, no classical one, but if you come to quantum mechanics and fiddle around with kinetic energy, then you can get it. Okay? But despite Earnshaw, might Lewis have been right? Might there still be shared pair bonds and lone pairs? What are bonds? Okay? And that's what we're going to try to find out. And how do you know? Or how do you know? How are we going to know whether they're electron pairs and whether that are shared between atoms and lone pairs on atoms? How can we find out? All right, you got to do an experiment. So what kind of experiment? Now these experiments are tough. Why are the experiments tough? Because things are, well, we could see or we could feel whether these electron pairs are there, right? But there's a problem, as you say, that it's inconceivably small, the thing we're looking for to see or to feel. Okay, but is it really inconceivable how small they are? I mean, when I was in your place, everybody thought, yeah, they're inconceivably small, we'll forget it, right? But there are more recent techniques that suggest that you can really see things that small, or at least you can think about them clearly, okay? Now, the first idea of seeing them came from this book here. Actually, this book was published, this is a third edition of the book. The first edition was 1909 and the second was 1919. And this is the third edition, which is still in print. You can go on the web and buy this baby. Occult Chemistry, a series of clairvoyant observations on the chemical elements by Annie Besant and Charles Leadbeater. So these are the occult chemists who started practicing their trade in 1895. Bishop Charles Webster Leadbeater, he was a bishop of a church he founded he was the head bishop. There were like 100 bishops and 500 members of the religion. This is Annie Besant, who is one of the most interesting people in all of history. They closed the stock exchange in India the day she died, for example. This is in the outfit she designed to lead the Boy Scouts in India. And she also proposed marriage to George Bernard Shaw. There are all sorts of interesting things about Annie Besant, but one of the things we're interested in is that she could see atoms. And then their helper, who became leader of the operation later on, was Jina Rajadasa. Okay, so this is a page from this book, from the paper that became the book in 1895, which shows what they could see for hydrogen, oxygen, and nitrogen. Now there are a number of levels here. The very lowest phase is solid, H-O-N, then liquid, then gas. So this is what, when they went into sort of a trance, they could see, right? This is the gas. But then there's ethereal 4, ethereal 3, ethereal 2, and ethereal 1 phases as well, that with higher and higher resolution you can see these. So these, for example, these little dots that you see here are what get blown up here. And the little things inside this are what get blown up here, and the things inside this get blown up here, and the things inside this are this. And that's the same for all atoms. That's the fundamental unit. Okay, so here's hydrogen at the gas resolution level. So there are wheels and wheels and wheels here. And here's what oxygen looks like. It's these little helices. Okay? And now that's the thing you finally get to, the thing called Anu. And that they actually ripped off from this book, The Principles of Color, which was published in America in 1878 by Edwin D. Babbitt. And here's his picture of this thing. And lo and behold, that's what they saw as the fundamental constituent of matter. It's fun to look at in detail. You can look at it at the web if you want to. It also has pictures of the angel of innocence here and the psychomagnetic curves surrounding your head. Okay. Okay, now lo and behold, the real confirmation of this thing was that if you counted up the Anu in the different elements, there were 18 Anu in hydrogen, 290 in oxygen, and 261 in nitrogen. And if you divide that by 18, you get the atomic weights. QED. Okay, so they have pictures in this book of a bunch of the atoms. This is helium, which has 72 Anu. This is lithium with 127 Anu. Not the bottom part. This is a model, and this is the wooden base it sits on. Here's iron, 1,008 Anu. Here's neon, 360 Anu. Now look at neon. And that is a 4F orbital electron density calculated by quantum mechanics. Now the question is, why would you believe me or believe a textbook or believe a quantum mechanician and not believe them? Because they said they saw it too. Okay? Well, it takes time. We talked about this before, the bases for scientific belief. Evidence, you always cross-examine an assertion. Logic, and taste. But taste matures with experience, and at the beginning you don't know which people to believe and which not to believe. That's a problem in politics too. Okay, there's sodium, 418. They not only said they saw atoms, they also saw molecules. For example, here is sodium carbonate. What do you see in there? Right? 2 sodiums, right? Okay. In the back are pieces of a carbon atom. What else do you see? There are 3 oxygen helices wrapped around the sodium and the carbon. And they wrote, note that this triangular arrangement of O3 has just been deduced by Bragg from his X-ray analysis of calcite. We'll talk about Bragg and what he was doing next time, right? But they have experimental evidence that supports what they're reporting, independent experimental evidence. Okay. Here's their model of benzene. And they say about that, each of the 3 valences of each carbon are satisfied by hydrogen. And the 4th valency, which some have postulated is going to the interior of the molecule, does actually do so. In fact, Annie Besant was the first woman to get a degree in chemistry at the University of London. But that's another story. Her teacher was the guy who translated Das Kapital into English and had a lot other nefarious things that he did. Question 6 will have to do with that. Okay, so here's benzene and its resonance. These were structures that were first early proposed. We'll talk about that later on. But some people didn't like this idea of going back and forth between 2 things. And they thought that you just have the 4th valence of every carbon going into the middle, right? All satisfying one another. So this was what they said that their model confirmed, that the 4th valence of every carbon goes into the middle. Okay, needless to say, most people nowadays don't think too much of occult chemistry, even if you can still buy the book online. Okay. This portal you came through this morning, it says erected 1921. But here's the same place in 1923 when the building was dedicated, and you notice those plaques weren't carved yet. It didn't say erected 1921. They were still finishing the building at the time the American Chemical Society had their national meeting here to celebrate the biggest academic building for chemistry in the world. Okay, so the slates were clean. Now, if you go down into the crowd here, you see some interesting people. For example, there's G.N. Lewis with his Philippines cigar in his hand. He always had a cigar. He smoked 17 cigars a day. Groan. Okay, but they were trying to decide how to decorate all these plaques around the building. And they wanted to put the names of distinguished American chemists. Had they done that, it would be pretty much a disaster because the people who were thought to be distinguished American chemists in those days were not so hot, actually, in retrospect. But they chose a wonderful group. And the idea came from Giuseppe Bruni from Bologna, who had come to the meeting to speak. And he said, don't put living chemists there, okay? Put dead chemists. And that's what they did. In almost all cases, they were dead. And it's a wonderful group, as we've already used Faraday, remember? Okay, here's one of them that's over in that corner of the building. And Van't Hoff, have you heard of Van't Hoff? You'll have heard a lot of him by the end of this semester. And Gibbs? Yeah, Gibbs, we'll talk about him too. And Mendeleev you've heard of. But I suspect that Crookes is not so familiar to you. This is Sir William Crookes, who was Fellow of the Royal Society and FTS. In 1861, he discovered the element thallium. He also developed a cathode ray tube, which he's holding there, which became the X-ray tube. And he invented the Crookes radiometer. I bet every one of you have seen a Crookes radiometer. Do you know? There's a picture of a Crookes radiometer to measure the intensity of light by how fast it spins. You've seen these things you buy in novelty stores that sit there and spin in the light. Okay. From 1913 to 1916, he was president of the Royal Society, the same thing that was founded back by Boyle, remember, and Robert Hooke and those guys? In 1898, he was president of the British Association for the Advancement of Science, and he was also in that year president of the Society for Psychical Research, right? And FTS is fellow of the Theosophical Society, right? In his presidential lecture to the British Association for the Advancement of Science, one of the things he said was, telepathic research does not yet enlist the interest of the majority of my scientific brethren. Okay? But he's the guy who supplied the samples for Leadbeater and Besant to look at. He supplied them with lithium, chromium, selenium, titanium, vanadium, boron, and beryllium samples so that they could draw these pictures of what they saw by clairvoyance. So you can read more on the web if you want to about him. He's an interesting character. And there were a lot of really serious scientists. Oliver Lodge was another one who invented radio and was head of the physics department at Bristol, I think, who was into communicating with the dead and stuff like that. So it wasn't obvious at the beginning who you should believe and who you shouldn't believe. Okay? But to get back to the point, and forget clairvoyance for a while, which I don't believe in, the question is, are molecules unobservably small for what Newton called vulgar eyes? Is there no way we can see something and measure it that's that small? So consider water. A cubic centimeter of water is an 18th of a mole, since the molecular weight is 18. That means it's 6/18 times 10 to the 23rd molecules in a cc of water. Now, that's a really, really big number, and it sounds like they must be just impossibly small, hopeless to try to see such a thing. But the difference is between the cube and the cube root. Because when we measure distance, we measure linear, not volume. So to get something about distances, you take the cube root of the volume. So if we take the cube root of that, it's about 3 times 10 to the 7th. Now that's still a very big number, 30 million, right? But it's not impossibly small. It's about 3 angstroms is this dimension, the size of a water molecule. Remember, we'll talk a lot about a carbon bond, carbon-carbon bond, being about 1.5 angstroms. Okay, now think about 10 to the 5th, okay? So this lecture room is about 10 meters wide, okay? One of my hairs is order of magnitude 100 microns in diameter. And that's a ratio of 10 to the 5th, right? So 10 to the 5th of my hairs sideways would go across this room. So that's a lot, right? But it's not impossible to think of lining up hairs to go across the room or putting them side by side. It'd take a while. But it's not impossible to think about that, a hair compared to the room, right? But a molecule is about a nanometer, and a small atom is about 1/10 of a nanometer, or an angstrom, right? And that ratio is 10 to the 5th. So the room to my hair is like my hair to a molecule, or even an atom, right? A big atom. So it's not impossibly small, it's just very, very small, okay? In fact, the nucleus is 10 femtometers, right? Which is another 10 to the 5th down. So that means if the lecture room were an atom, the nucleus would be the diameter of a hair, right? Very small, but not impossibly small to conceive of, okay? Now, Newton in Optics, the book we looked at before in 1717, wrote on page 369, the thickness of the plate, where it appears very black, is 3/8 of the 10/100,000th part of an inch. That means he knew the size of it. Now, how big is 3/8 of the 10/100,000th part of an inch? Well, 10/100,000 is a million, right? 3/8 of a millionth of an inch is 30 water molecules. So somehow Newton was able to measure something in 1717 that was the size of 30 water molecules. Now, what tool could Newton possibly have had in 1717 that allowed him to measure something so very small? What? I can't hear very well. Glass springs? Ah, right. That's right. Okay, so here it is, Newton's rings, which really should be called Hooke's rings, because he's the guy that in micrographia that published how they work. But remember, they had different light theories. So here are two pieces of glass, 2 discs of glass, and I'll change the light so we see light through them. And Now I can't remember which is which. But let me guess that if I put this one over here, having turned it over, that, and press on it some, not see anything yet. Okay. Oh, I can see it here. Can you see? Yeah, you can see. See those patterns? You've seen things like that with microscope slides, colors. Okay? So these are two flats against one another. They get very close to one another. But if I turn the top one over, you see that it's a little bit, so that's what we just saw. But notice that if I turn it over, there's a little, there turns out here at the edge to be a little bit of a gap because the top one is just very slightly curved. And now let me see if I can see something here. Can't see it yet, let me zoom in. And we're going to need to focus on that. Okay, now let's watch. Ah, see that thing? See that? I need help. Will you come up and help me? So you need to zoom in while I'm trying to keep that thing in the middle.
Where do I zoom?
It's right, see it says zoom plus over here?
Yeah.
Okay, zoom in on that. Okay, there. Now the autofocus is zooming in and out on this. In fact, we've lost it. Let me try something here. Oh, you see it? There. Okay, so so here's what you're seeing. In the middle is what's called Newton's rings. They look like that. Different colors, right? And Newton could measure the thickness of the air gap that caused different colors. The colors repeat, right, in higher orders. Okay? Now, how could he know the distance? So he could associate every color with a distance. How could he know the distance? Because he could measure the diameter of the rings. And he said this, observation 6. The diameter of the sixth ring, right, 1, 2, 3, 4, 5, 6, at the most lucid part of its orbit was 58/100ths of an inch, and the diameter of the sphere on which the double convex object glass was ground was about 102 feet. Hence, I gathered the thickness of the air or areal interval of the glasses in that ring. So in other words, here's the air gap he's trying to measure, which is the sixth ring out, right? He knows the diameter of that ring. He knows that they touch in the middle, the two glasses, right? And he knows that it's a sphere and that it has a radius of 51 feet. So he can just use trigonometry to figure out that the air gap, if he knows that angle there, the air gap is 1.8 microns, right? So that's a lot bigger than an atom. But if you go into the first ring, or even closer, then you can measure it, right? So all he needed was a spherical glass with a very large radius, and he could measure these distances. Okay, but here's the simpler measure of an even smaller distance, about 100 years later. And here's the guy who did it. You know who that is? Benjamin Franklin, of course. We'll get back to the artist later on. So he published in the Philosophical Transactions of the Royal Society in 1774. The society is now 110 years old, 114 years old. This article on the stilling of waves by means of oil. Can you see what that means? What's that related to, a common saying?
Separation.
Pouring oil on troubled waters. Have you heard of that one? So the stilling of waves by means of oil extracted from sundry letters between Franklin and Brownrigg. Okay? So he wrote to Brownrigg, 1773, I had when a youth read and smiled at Pliny's account of a practice among the seamen of his time to still the waves in a storm by pouring oil into the sea, as well as the use made of oil by the divers. Pearl divers would fill their mouth with oil, and when they went down, if a breeze came up and ruffled the surface, which made it hard to see because the light wouldn't come through clearly, then they'd let oil out of their mouths that would float to the surface, stop the ripples, and they could see to get their pearls. This is what Pliny said, right? But he said he smiled at that. What a quaint thing to think, right? It's like the occult chemists. I think that it has been of late too much the mode to slight the learning of the ancients. The learned, too, are apt to slight too much the knowledge of the vulgar. Okay? In 1757, being at sea in a fleet of 96 sail bound against Louisbourg off Cape Breton Island, I observed the wakes of 2 of the ships to be remarkably smooth, while all the others were ruffled by the wind, which blew fresh. Being puzzled with the differing appearance, I at last pointed it out to our captain and asked him the meaning of it. "The cooks," said he, "have I suppose just been emptying their greasy water through the scuppers, which has greased the sides of those ships a little." So there's experimental evidence for what Pliny said. Okay? Recollecting what I had formerly read in Pliny, I resolved to make some experiments of the effect of oil on water when I should have the opportunity. And when he had the opportunity was when he was in London. So here's London, and his experiment in 1762 was in that place on Clapham Common in South London. At length, being at Clapham, where there is on the common a large pond, which I observed one day to be very rough with the wind, I fetched out a cruet of oil and dropped a little of it on the water. I saw it spread itself with surprising swiftness upon the surface, but the effect of smoothing the waves was not produced. So the experiment was a failure. Okay. 4, I had applied it first on the leeward side of the pond where the waves were greatest, and the wind drove my oil back along the shore, so it didn't spread on the surface, right? So what did he do? Go to the other side, right? I then went to the windward side where the waves began to form, and there the oil, though not more than a teaspoonful, produced an instant calm over a space several yards square, which spread amazingly and extended itself gradually till it reached the lee side, making all that quarter of the pond, perhaps half an acre, as smooth as a looking glass. So a teaspoon is 5 cubic centimeters, and he stilled half an acre, which is 2,000 square meters, okay? Which means that the thickness of this layer, right, to spread that many cubic centimeters over 2,000 square meters, would be 25 angstroms, which is the length of a molecule of the fat that's in the oil. So Franklin had in fact measured the length of an oil molecule in this way, right? Now, he didn't think he had measured it and didn't claim to have measured it. He said, when put on the water, it spreads instantly many feet around, becoming so thin as to produce the prismatic colors, the Newton rings colors, right? For a considerable space, and beyond them, so much thinner, it became so thin that you didn't even get Newton's colors, right? So much thinner as to be invisible, except in its effect of smoothing the waves at much greater distance. So the technique was stilling the water, right? Allowed you to measure how big the area was. Isn't that cool? Okay. It seems as if a mutual repulsion between the particles took place as soon as it touched the water. That is, they pressed one another apart and moved. So what he wouldn't have known was that they pushed one another apart, but they stayed in contact with one another, right, to become a monomolecular thick layer over the water. So he didn't claim to have measured it, but indeed he did measure the size of an oil. So these things are the size of an oil molecule. So molecules are very, very, very small, but they're not inconceivably small, and there are ways you can measure them. Okay. So we have this question, are there electron pairs? So let's try first feeling with scanning probe microscopy, or SPM. Can we feel individual molecules? Can we feel individual atoms? Can we see what bonds are by feeling them? Right? So scanning tunneling microscopy was invented in 1981 by these guys in Zurich, Gerd Binnig and Heinrich Rohr. And here's the first publication. They worked at IBM. And here's the first publication on the cover of their journal about a meeting about this new technique, scanning tunneling microscopy. And they got the Nobel Prize within 5 years, or maybe it was even less, very short order, 1986. Okay. Now, how does that scanning tunneling microscopy, which is one type of SPM, scanning probe, scanning tunneling is one way, and I'll mention that shortly. But first I'm going to talk about atomic force microscopy. And for this, you need a little chip, and I'll show you. The chip is in here, in this little bug box. You can't see it here. Well, there's the chip in the middle, right? And I'll pass it around so you can look at it. And if you tilt it so that the light from the ceiling glints off the gold, and you see it really shiny, you may be able to see at the thin end these little V's. Okay? You can see here at the bottom little V's. The chip is 1.4 millimeters wide. It's a gold-coated silicon chip. And if you look at those with even higher magnification, you see this, and there's the size of a hair. You can actually see, did you see them? They're not easy to see, and maybe you will, maybe you won't, but they're there. Okay, so there's the size of a hair. And in any given experiment, you have a choice of 5 different cantilevers, as they're called, that you can use. Okay? Here's a higher resolution electron micrograph that shows the tip of one of these V's, and you see a little bulge here at the bottom. And if you zoom in on that, you see this. It's a little pyramid. And so at the bottom of that pyramid, the radius of curvature of this tip is only about 20 nanometers, so about the size of 20 molecules, right? It's round on the tip. It's not truly pointed to come to nothing, right? It's a little bit rounded. You can buy ones that are a third that size, their radius of curvature. Okay, and then you have this piece of glass. I said do not touch when you came in because that piece of glass cost $2,000. Let's see, you got to back up here. Okay, so there's this piece of glass, and if I hold it up here, there's a little chip on the bottom of the piece of glass. I know what I'm looking for. I don't know if you can see it or not. But anyhow, it's held into this piece of stuff here. And those little tips are pointing up here, but in fact the thing is used upside down, so they point down. So here's that thing mounted in an instrument, and you see there's a red light glowing in the glass. And the reason is it's being irradiated by, so there's a blown up picture of one of these tips pointing down. And laser light comes and bounces off the shiny gold on this tip and gets reflected up to a detector. Now, what would happen if you pushed up on the tip? It would deviate the reflection, right? It would go like this. And you have a very precise position detector for the laser light up where you see it, the light glowing. So you can tell the deviation of that tip moving up and down by a size that's less than an atom. Isn't that neat? So now what you do in this is move this back and forth over the sample and watch the little needle go up and down by the reflection of the light. So if the surface was like this, it'll go click, 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 up, 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 right, as you scan across, right? And it's sensitive, as I say, to less than 1 molecule change in height. Although it doesn't feel an individual molecule, because the tip, remember, is 20 nanometers wide, right? So the width of the tip is like 100 or so atoms, right? So it's touching a bunch of atoms at any one time. But if you come to a ledge on like a crystal, it would be going at a certain height, touching a bunch, and then it would move up and touch a bunch more. And you'd be able to tell that it went up and down if that distance was only one molecule. Easy. Here's, in fact, a picture taken by an undergraduate. In fact, it's a movie. So it's AFM traces. So what you do, it's like a TV, you know, where you go zoom, 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 and then you go back to the top, zoom, 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 say how high it is at every point along the scan, and then color code it to show how high. So the width of this is about 600 molecules, right? But the lines you see, which are ledges that go up and down, each of those ledges is one unit cell, 1.7 nanometers, one set of molecules. So these are, and the top surface where it's flat is absolutely flat, right? Except for there's little holes there. And those holes were made by taking this tip and pressing down and scratching a little bit to knock some of the molecules away. So that the larger pit is 5 nanometers deep, which means it's 4 layers of molecules been knocked off in there. And now this is underwater, or underwater in propanol, so the crystal is dissolving slowly. So those pits open up as molecules come away. So watch. Right? Those are at 1 minute intervals. So we're actually feeling individual molecular heights with this thing. There was an interesting point here that I'm not going to dwell on, but the smallest one did not lose any molecules. If I back up, watch the smallest one. It always stays the same size as the others dissolve. That's an interesting puzzle, isn't it? But at any rate, you can do it. And you can measure the rate at which different ledges dissolve. Some dissolve much faster than others. Here's a scanning tunneling microscopy. This is done a different way. It's not, you don't reflect the laser light. What you do is detect the electrical conductivity through a layer. And if you have an atom there that is a good conductor of electricity, you get more current through and less and so on. So as you scan now this could be a really, really sharp tip where the tip is just one atom or a couple atoms. So now as you go across, you can feel things that are much smaller laterally, okay? So this picture here, that thing right there, which is, as you see, a repeated pattern, that's one of those molecules with C12 in it and a bromine on the end. And here's a model that shows what the molecule looks like. The yellow is bromine, the brown are the 2 oxygens, and the green are carbon and the gray are hydrogens. They don't come colored that way. They come looking like this as to conductivity. But you can see individual atoms, right? Or one of the more dramatic early examples in 1993 was at the IBM labs at Almaden in California, where they worked on iron atoms on a surface of copper. And they used this tip and changing the voltage to pick up atoms and move them where they wanted, then change the voltage and drop them there, then go back and get another one and do it. So they made this thing they called a quantum chorale of whatever, 58 or something iron atoms. Yeah.
Is that along the lines when they move?
Pardon me?
Is this along the lines when they move the atoms and spell out?
Oh yeah, they also spelled out IBM, right? They knew which side their bread was buttered on too, just like the Royal Society did. Okay, so that's neat. So clearly you can see or feel individual atoms, right? But you don't see the bonds. The bonds are smaller. It just looks like a bunch of balls, right? You don't see the electron pairs between them. Here's SNOM. SNOM stands for Scanning Near Field Optical Microscope. So this is in a sense seeing. But actually it's scanning, it's like feeling. So what you have here is a glass fiber that's drawn down to a very sharp point and coated with aluminum. And the hole at the bottom is just 100 nanometers. That's like 100 molecules, right? Not really, really tiny like the scanning tunneling microscope. So what you do is you have something on the surface of a slide there that you want to probe with this, and you send light down the thing. And if there is a molecule where the light's coming out through this tiny hole, if there's a molecule there that will take the blue light and emit red light, then you know when it's under the tip. Suppose there was just one molecule on the whole slide. You scan it around until suddenly red light comes out. Then you know that tip is pointed toward that particular molecule. Okay, so red light comes out and you have a detector that detects it, and you scan the sample back and forth like a TV, right? And you find out where such molecules are. And here's a picture taken in that way. So this is a scale of microns, right? 2 by 2 microns. In fact, it's a distorted scale, as I see here. Okay, and that arrow, double-headed arrow, is the wavelength of red light. So you're seeing things significantly smaller than the wavelength of the light, having done this way. You're not really looking with your eye, you're doing this scanning trick, right? Okay, so scanning probe microscopies like atomic force microscopy, scanning tunneling microscopy, scanning near-field optical microscopy are really powerful, and you can see individual atoms, right? The sharp points can resolve individual molecules and even atoms, but not bonds. So it's not doing what we need to do for our purposes. Now, that's, I'm going to spend the last few minutes going over the problem that we were looking at with, remember you were supposed to draw all the resonance structures for HCON isomers? I think you remember that. Okay, so let's just look at it. So what we're going to do is compare what we see with Lewis theory with things that have been calculated by reasonably good quantum mechanics, not the very, very highest level, but pretty good level. Okay, so we want to try to make all the possible arrangements here. So we can put the 3 atoms, OCN, with any one of them in the middle, and then we can put hydrogen on either end. Right, so then we'll do it with nitrogen in the middle, then with oxygen in the middle, so we'll have done all possibilities there. So here are 2 possibilities. Now, are these good structures is what we have to decide. Okay, now, it would be possible to shift electrons here and draw a different Lewis structure. Which of those 2 do you think is better? Why? Okay, there's separation of charge on the bottom. Okay, so there's bad charge separation. The most electronegative atom, oxygen, in fact has a positive charge, not a negative charge, right? So that's, not only is there charge separation, it's in the wrong direction. But they're all octets that we've drawn in both structures. All atoms have octets. Now let's try the same trick over here. We can do it that way. How about that? Which of those is better? In both structures, we could go through and count and see that they're all octets. Right? Would you like me to do that, or is that something that's become second nature to you by now? Does anybody want me to count them? Okay, you got that. But now, which of those 2 structures do you think is better? And okay, so you say the top one's better, you say, because it doesn't have charge separation. Now, as compared to the case on the left, which do you think, if you have to have charge separation, which one is better? The one on the right, because at least you have it with the right atom, the oxygen being negative. You could have drawn the one on the top too, right? And that goes the other way. If I drew, notice that I've introduced something here that I haven't really talked about enough. The idea of curved arrows. Curved arrows show a shift of electrons, right? An electron pair. What would you draw if you wanted to show just one electron shifting? If you had to think up the notation. Dotted curve would be one possibility. Another possibility, Sophie? Had like a fish hook instead of a double arrow, right? And that's in fact what's used. If you want to shift just one electron, you show a single barb, and if you do a pair of electrons, you show a double barbed curved arrow. So curved arrows don't show atoms moving. They don't show this atom goes to there. they show an electron pair moving, or sometimes a single electron moving, and you can use a double or a single barb to show which one. Okay, so get that straight, because that's often a problem. Okay, so the one on top is much worse than the one on the bottom. Okay, so there are possibilities with C in the middle. Now, how about if you put N in the middle? Here are two structures with octets. Now, pardon me, they don't all have octets. That one on the right has a sestet, right? Because the carbon is making two bonds, so it gets 3 electrons out of those 2 bonds. Pardon me. It gets 2 electrons out of those 2 bonds, one from each bond that's its share in the bookkeeping, plus an unshared pair, right? That's only, well, I mean, what's associated with it, it has only 3, pardon me, I'm saying the wrong thing here. It has 4 electrons that it calls its own from bookkeeping point of view, 1 from each bond and 2 in the unshared pair. So it's not charged. It came in with 4 electrons. It's still got 4 electrons, but it participates with only 3 pairs of electrons, so it's a sestet. So that's not so good on the right. The one on the left is not so good because it's charge separated. At least it's on oxygen, right, the negative charge. We could draw this other one, which puts the negative charge on carbon. That's, we would say, not so good, right? So that's a bad charge. Or we could do it that way. That looks like the best charge, probably. Better to put positive on carbon than on nitrogen. Okay. But that carbon has a sestet. The others are octet ones. Okay, and we can do this other one over here. Now we've got an octet on the carbon, but we got negative charge on the carbon. That's not such a great charge separation thing. Or we can do it this way, but again, we got bad charge. Okay. So now if we put O in the middle, we can do these structures, both of which you notice have, what's bad about them? Sestet there, sestet on the right too. There's a plus charge on oxygen. That's not so great. You can draw curved arrows and shift the electron pairs around. You now got an octet on carbon, but you got a sestet on nitrogen. And bad charge, negative on carbon, not so great. And over here you can do that, sestet again, bad charge. Or you can make the 3 heavy atoms into a ring, and then you could put the hydrogen on any one of the, coming out of any one of them. Now the one on the left, with my computer, I can't calculate it. I can't find an energy minimum that has that structure. So that one is very bad, which doesn't surprise anyone. It's got horrid angles for the bonds, although we haven't really said that we prefer one angle over another. But it also has bad charge separation. Okay? That one's a bad charge, so we could draw this other one here, but still got positive on oxygen, sestet. What do we have here? Sestet on carbon. Okay, so here are the bunch of isomers we've just gone through, right? Now, a couple of years ago when I first talked about this in the class, and when these things had been accurately calculated, or as accurately as people are likely to do to calculate their true energy and structure, I tested my colleagues in the department to ask them if they could rank these things as to what's the lowest and what's the highest energy and so on. And no one succeeded. In fact, only a few people know which the lowest one is on the basis of their familiarity with Lewis theory. So the point is, don't be depressed when you are trying to do this. It takes a lot of lore, and even with all the lore that's been gathered over many years, people can't use Lewis theory for this purpose because it's just not that good. Okay, but in fact, the way I've drawn them there is their energy, according to these pretty good calculations, right? The very lowest energy is the C in the middle and H on the nitrogen, and then C in the middle and H on the oxygen. Now, you can go back and look at what we said was good and bad about these things and convince yourself that, now you understand why those are on the bottom and these are on the top. But if it had come out differently, you would have convinced yourself differently. Okay? So that's enough for today. actually, there's a reference for this if you want to see it. The energies were published in the Journal of Chemical Physics in 2004.